All right, welcome everyone to our third workshop in the advanced track series for winter 2022. Glad to have you all back after like I guess 1 week like hiatus of a sense because of MLK Day. Hope you guys all had a good one of those, a good MLK Day as well. Today we'll be talking about a type of neural network called a convolutional neural network. It's a really, I guess, important and also like often used type of neural network in industry, and so it's really essential that to understand both how it works, but also how to use it. And so we'll be going into that in this workshop. Again, if you haven't joined the Discord, please go down and click the link right here, bit.ly/ACM Discord, so that you can join the Discord, because that's where we post both announcements as well as recordings of prior workshops. And also, again, we have our feedback form here, and it's also where the slides are. So if you go to the feedback form, the slides links will be there as well. We really appreciate your feedback. So if you can leave feedback eventually at the end of the workshop, that'd be great. All right, so quick breakdown for today. First, we're going to review last week's recordings content a little bit, not too much, but we'll talk about the main essentials of that workshop. Then we'll go into a bit of the applications of CNN, so where they're being used today, as well as like some commonly used like applications that use CNNs. Then we're going to go down into the actual theory and intuition behind CNNs. So that goes into like a brief review of like exactly, like I guess like a more broad scope of what it is, and as well as like exactly what makes it. So the convolutional layer, which is one of the most important parts of the convolutional neural network, as well as the other layers that help facilitate this layer. So first, reviewing last week's content, which is the fully or V4 neural networks, or fully connected. And so I'm going to go through these slides real quick, or at least there's like about 4 or 5 slides here. So I'll go through them, and at the end, feel free to ask any questions that you have from last week's recording, and we can go through those at that time. So first, I guess here's like a blueprint about how this type of network generally trains. And so remember, training is how we make the model better over time. And so first, we define an architecture. So in week 2 or last week's recording, it was fully connected networks. Then we determine the number of inputs, hidden layers, and outputs. So inputs being like what we pass in, hidden layers being like the layers in between that do calculations based on weights and biases, and then outputs being like what we want in the end. Third, we initialize weights and biases. So we set them according to some either random or initialization process. So these initial weights and biases aren't very good, but we're going to make our model better through the training process. Then we went over a really important process last week, or in the recording last week, called feed forward. And so feed forward is how basically we use our weights and biases given some inputs to create a certain output. And then we use a loss function to actually compute a loss on our model, given some examples. Then we determine the error from that loss. And then the next big part of neural networks in general, we backpropagate. And so basically this is using our loss function or cost function, same thing. And that it uses that cost function to basically change the weights of all the layers in our networks, not just the output layer, but all the layers. And so this is basically what the 6 and 7 are. We backpropagate using some gradients, and then we're going to update our weights and biases using those gradients. And so breaking down the 2 main components of this are feed forward and backpropagate. First is feed forward. So feed forward, you can think of as the process where we take our inputs in and then use our weights and biases to actually get our outputs. And so it's fairly similar to what we had in logistic regression. However, on like a more of a, instead of individual node scale, more of a layer scale. So many nodes in like a certain layer. And so first, you can see the equation up here. We covered exactly how we got to this in our recording last week. But if you remember, at least logistic regression, there's a lot of similarities here between weights, previous inputs or previous layer, biases, activation function, and current layer values. And so we can see here that like this formula is really familiar to us, and like basically we're expanding upon it for deep neural networks. And so basically this formula allows us to both compute outputs, but also allows us to use those outputs to eventually compute a cost for our network. And so this formula is both essential to creating our outputs, but also to making our model better. So now backprop. So backpropagation is basically looking at our original loss function and basically propagating the error backwards depending on how much each weight or bias impacted that. So we went into that into more detail last week's recording, but to essentially summarize it here, we have our cost function. And so we're going to take our gradients or our partial derivatives, and we're going to use those to basically update the weights and biases. And we're going to do that across all of our layers, which is why it's called backpropagation, because we're propagating backwards through our layers and updating the weights and biases based on their partial derivatives. So that was a lot of content. Again, lots of it was covered in last week's, I guess, recording. I just want to break here and ask, anyone have any questions in general from the recording from last week or from what I just covered? I guess if it was confusing at all, feel free to go to last week's recording and watch it again as well, if that's more helpful. But any questions at this point? Yeah, Jeffrey, go ahead.
I noticed that you keep using the words loss and cost, and I was wondering if they're interchangeable in this context.
Yeah, so in this case, yeah, they are basically interchangeable. Yeah, it's basically the same thing. Difference between, so in the chat, Margaret asked, what's the difference between error and cost? And so see here, so I guess, yeah, it is important if we say that backpropagation of error is compared to cost. And so I think we covered it more in detail, and I guess in the previous recording, but we see here that cost function is basically, it's similar to what we had, I guess, in beginner tracking, that where we're taking basically a version of a mean squared error right here, and it's our cost function. However, error, I guess, I would say it's more in like a individual, I guess, individual weights and biases terms context. And so I guess in this case, we're looking at cost of our overall thing, and it errors in terms of like how much our weights and biases are, yeah, call correctly. Yeah, exactly. So basically, as Terry said in the chat, I think it's way better than I explained it exactly. Yeah, but basically, the entire function is a cost function, or like the entire network is a cost function, where like we're looking at how the outputs and inputs, or how the outputs and the actual true values compare, and then each weight and bias has like an error which we want to correct and get towards the optimal value. And so we use these partial derivatives to update to correct those errors. A great question, yeah. Anything else? All right, cool. So again, feel free to interrupt me if you have any other questions, and we can go over that at that time. All right, so now moving on to CNNs. And so now that we have the necessary background on, I guess, in general, how neural networks work, as well as fully connected neural networks, we can move on to CNNs. And so CNNs, they have a lot of really cool applications. A lot of them are with respect to image classifications and image like processing in general. And so a good example of that is using it for self-driving car predictions. And so as you can see in the picture right there, we can use convolutional neural networks to basically identify objects in a certain image. And so you can see here that given some input images, as well as like some, I guess, different versions of that input, like different, like, I guess it's the readings of the input or whatever. We have different inputs, and then we will use convolutional neural networks to basically figure out, I guess, where are certain objects in this thing. And so you can see on this the bottom left side, the network has identified many different objects that are present, like a human here, something in the background, like some poles and trees here. And then it went a step further and also actually predicted, I guess, riskiness of different objects in that thing. And so it's learned through training basically how to process a general image and also to figure out, I guess, general risk and ascertain general risk in terms of objects. And so you can see here, CNNs are really powerful due to their ability to process like a really common source of data, being images. Another example is I guess it's Meta now, but Facebook using convolutional networks to basically tag people in posts. And so basically think of this as basically really fast facial recognition. But the way to do this is with convolutional networks. And so this is really cool, and also probably something that you've interacted with many times, is because we've all either used Facebook or Instagram or something of that sort. And so this automatic tagging is thanks to the power of convolutional networks. So those are a couple examples. I'm sure there's a lot more as well. But now that we have some idea of exactly how powerful CNNs are, we can go into a bit more detail on like what exactly we need for CNNs. And so first starting out with what exactly is a CNN, I guess this is a pretty, I guess, broad definition of what it is. And so you can think of it as a mostly used for computer vision. And so these, as a result, it's often used for classification using convolutional layers. And so we'll get into exactly what those are in a second. But basically, using those layers to basically find like certain really important features in images and thus abstract them or like rely on those to classify images or classify certain things in images. And so you can see in the previous examples that we actually use certain features to identify like people or identify objects and riskiness of objects. And so CNNs are really powerful for basically looking at big sources of data, and then as a result, using them to basically concentrate on a couple more complex, higher level features, as I said here. And so I guess some more, we have about neural networks. And so we see, so let's say we have a single image only, right? Don't forget about having a huge data set. We only have one image. And so we have a single image. And we know what neural networks and in general machine learning, we want to think about this in terms of vectors and matrices, right? And so again, we can have our image be a matrix of values or a 1D vector of pixel values actually to be squish it into one vector. So we can squish our picture into a one input vector. And so this is what we're going to be dealing with in general for our old neural networks. So remember, fully connected networks, they mostly work with vectors. And so we'll need to squeeze our array of, or like our big picture into a 1D array of pixel values, and then use that in collaboration with our weights, our matrices of weights, to make a network. And then as a result, multiplying a matrix by an input vector will return an output vector, which will pass on between layers. And so in general, think of our images or our inputs as vectors, and think of it as like using matrices, multiply that and like pass on that data over time. And so seeing that right here in general, similar thing. So this would be a really small image, like a 1x3 image right here. We have our weights matrix right here and see that it's a fully connected network. So each node in the first hidden layer is connected to each node in the input layer and so on. And so we have our matrix right here, as well as a bias vector that we use to multiply by our inputs to calculate our next level. So remember, we talked about feed forward. So we'll be using that same formula here to calculate our next level, our second layer, as well as third layer, and then finally our output layer. And so CNNs don't work in this exact same, I guess, environment of like vectors and like matrices times vectors equals pass output vector. So CNNs work with these things called volumes. And so you can think of this as sort of a tensor in its way, so a three-dimensional, I guess, matrix. And so in general, we'll be using three-dimensional things, but also more dimensions can come into play. And so you could think of it as like our images are going to have a height, a width, but also a third dimension, which it's usually for color channels or certain channels. But let's say for now that we have 3 channels for red, green, and blue. So typically images are use RGB for I guess conveying color, and so we can use those 3 as 3 different input levels or depth in our 3rd dimension. So in general, we have 3-dimensional inputs, and so it's important to distinguish that with CNNs, we're thinking in like a 3-dimensional space rather than like a 1 or 2-dimensional space. And so this can be kind of complicated at first, especially if you have a 3rd dimension with I guess size 3. So to start with, we'll be talking about having like monochrome inputs. So basically, this 3rd dimension is going to be size 1, and so we're going to have height width by 1, and so you can think of it as kind of a grayscale image in a sense. And so building on top of that, neural networks, like neural networks or regular neural networks, CNNs are also a combination of many different layers. And so building off the concept from that previous slide, instead of having each layer have a matrix and then take in a vector and output a vector, we're gonna have every layer take in an input volume, so basically an input height, width, and 3rd dimension, and produce a certain output as well. And so each layer is going to modify that, I guess, that volume, and then spit it out for the next layer. So you can see here, basically, you can think of this as a way of visualizing how exactly certain layers might modify an input in a sense. So going into more detail of exactly how CNNs are usually structured as like a high level, we have a couple of different layers that we're going to go over today. So just recapping or giving background on all of them. The first one's called the input layer. And so this is what you might expect it to be, basically taking in the image and taking it as input and then passing on to the next layer. So pretty straightforward, just taking an image, a 3-dimensional input. Next, we have our convolutional layer, which is, I guess, a huge chunk of exactly what we're doing. And so that's going to be creating a feature map. So basically creating a section of like which pixels and which features have which features. And so you can think of this basically as like the really important, I guess, feature recognition part of our network. We're also going to have an activation function called Rayleigh, which we'll get into, a rectified linear unit. And so it's a commonly used activation function, which we haven't talked about yet, but we'll go into exactly why it's super useful. Then we'll talk about pooling. And so pooling is a way to basically downsample or basically shrink the size of our volumes to a more manageable size, and thus reduce some of the possibility for, I guess, over analysis of our data. And so like, I guess, simplify our data to make it easier to understand. And then finally, we have our final layer, which is going to be fully connected. And so this layer is basically going to be used to basically take all the stuff from before and then classify it into a certain class. For example, like if you have n classes, we're going to say we're going to output an n-dimensional vector, and whichever, I guess, slot in the vector has the highest value might be the actual class that you're predicting in. All right, so mapping this out more, we have a couple of different sections. This is a way of thinking about it. We have inputs, and then we're going to pass that in to our convolutional network. We're going to do our convolutions on it, apply Rayleigh to that, and so basically applying an activation function to a layer, which we know is commonly done. Then we're going to downsize it, or basically make it simpler with a max pooling layer, so a version of pooling. We're going to take all of that, and we're going to pass it to our final layers of fully connected layers, which in combination with Softmax will allow us to create an output vector to classify our input. So looking at it from the bottom now, we see that right here, we have an input image. We might have some convolutional and pooling layers right here. So we have convolution pooling. So you can have more than just one convolutional layer. And so as you see here, we're passing this image through multiple convolutional layers and pooling layers. And also in between, there'll be values in between these layers, as seen up here. And then after we've done a couple of iterations of convolutions, we're going to move on to our fully connected section. which will eventually give us some 4 outputs, which will be probabilities of it being a certain class. So you can see here that at the end, we have like a really small probability of dog, cat, and bird, and a really high probability of boat. So we're gonna say this is a boat given this output. And so in combination, these layers can take in like a really complicated, I guess, input, like a boat, like an image of boats, but also other things in the image, and then narrow it down to actual classification. Any questions about the general architecture stuff so far? Any of the layers and stuff? We'll go into more detail about it soon, but any questions about that? All right, cool. Feel free to ask questions, of course, as always. And so building off of that, we have, I guess, we're gonna move on to exactly the fact that like not all layers are built equal. And so we saw it in that previous slide. We had many different types of layers that all do different things. But before this week, we have only seen one type of layer, which is like a fully connected layer. However, we want to be able to do more complicated operations, and thus this has motivated a need for other layers like convolutional layers, pooling layers, and of course our fully connected layers, of course. But there's other layers out there that are really important to understand to, I guess, broaden the scope of what we can do. I guess I had a question slide here too. But any questions about, I guess, setting the stage for what CNNs are in general, or yeah. Are there any future use cases that are beyond image classification? Yeah, great question. I will say image classification is a pretty big field. I guess images are, I think, the most common use of CNNs. You don't have to only classify things, you can also do other things with images, like image generation, for example, or image like anomaly detection. So things like creating your own images or figuring out which image is very different from other images are also things. I think in general, the industry, yeah, like Preetam said, in general, speech recognition or text classification, those are also potential examples for CNNs. I think in general, the industry has gravitated towards image classification due to how useful it is in general for many different tasks. We're like, a lot of things that we do as humans are image based. And as a result, understanding images is really valuable. And so I think networks have been, I guess, fine-tuned in that direction or focused in that direction for those problems. But there definitely are use cases that are also really cool. And so, yeah. Jeffrey said too, video generation. So yeah, image generation, video generation. So there are a lot of different applications. And so, yeah, it's a good point. It's not just image classification, but what's one of the main uses of it? But yeah, great question. All right, let's move on. Wait, am I misremembering something? Okay, wait, am I on the wrong side? Apologies, everyone. I have become incoherent of slide numbers. Yeah, thanks for the reminder, Angela. Yeah, my bad, my bad. All right, sorry about that, guys. I thought I miscounted slides in my head. All right, sorry about that. Let's keep going. And so now we have, I guess, the question of CNNs seem really complicated. Like we have like 4 different types of layers, a bunch of different layers being combined. like, why do we need that if fully connected layers are super useful? And we just classified image. We can classify like images like this with fully connected networks, right? So like, what's the need to actually build beyond that? So you can see here that there's a common data set called MNIST, which basically is a bunch of handwritten digits, right? Like this number 8 right here. And so you can see here that even with a fully connected network like this, you can use this to actually classify images like this 8 or any digit to pretty high accuracy. So you might wonder why exactly we would want to have like, I guess, like anything beyond this. And so as you can see here, here's a network structure in general. We have 784 inputs. We have fully connected layer 1 and an output layer. And this is, I guess, a way of visualizing the weights as well of the first layer. So this middle layer in between. And as you can see, it kind of has a bit of like some features, but mostly looks like kind of randomness. And so that brings us into the downsides of fully connected layers. And so we see here that there are some, like, I guess, similarities of 8 here and stuff like that. And there's some things, but one of the main things is that this image right here, these images, they're all only 28 pixels by 28 pixels wide. And so while it's easy to figure out connections between, I guess, while it's easy to analyze really small images with fully connected networks, they don't. This approach doesn't scale well with larger images. Anyone have any ideas on why a fully connected network might not scale as well for image analysis? Any guesses, or feel free to put them in chat or unmute and say them. Can be a guess too. We haven't covered exactly why. Only so many outputs. So what do you mean by that, Jeffrey? Only so many outputs? Like, oh, we have a limited number of output nodes. You mean like that kind of sense? I guess. Yeah, I guess so. So, like, I guess you are stuck with a fixed number of outputs. But remember that our CNNs also have a fixed number of outputs as well. They're at the end of our CNNs. We also have a fully connected network that's going to output to a certain number of nodes. So our outputs can be kind of fixed to a certain size no matter what. Margot says, "Oh, they lack a third dimension for RGB." Yeah. So if like that is an important point actually. So like in the case where like color of images can really impact like what the image, I guess, conveys. So for example, like black and white images don't convey the whole message of an image. Like that third dimension could be really important for, I guess, color. But I'm looking for something a bit different. That is a good point though. So what I'm looking for exactly here is that, yeah. And so the fact about, I guess, fully connected networks is that they aren't as good at like analyzing certain pixels in relation to other pixels, right? And so when you look at an image, right, you don't look at every pixel individually and not consider things around it, right? Because every pixel individually is kind of incoherent by itself. And so this is the reason why fully connected networks don't scale higher with larger images, because you need to understand the context around a certain pixel to really understand it. And so CNNs do that, while fully connected layers don't do that. But great ideas though. It's it was a hard question, but I'm glad to see you guys are thinking about it critically. Yeah, so that's that. And then second example is that it's sensitive to translation. So we have here the really funny example of the same cat being shown, but like shifted over from like the right corner to the left corner. And some fully connected neural networks will classify one of these as an actual cat, but the other one not as a cat, because of the fact that there's different weights being applied to like pixels on one side compared to the other side, right? So maybe it's weighing the weights on the right side of the picture really highly for cats, right? But not the left side, right? So moving the cat from the right side of the image to the left side of the image will make it so that network no longer recognizes it as a cat, even though it's clearly the same cat, just shifted over a bit in the image. And so while these two problems are only like, I guess, two CUDA problems that we could mention, they are really big problems that are like, I guess, often encountered with images. So it's really important to understand that we need to like fix this. Yeah, okay, last slide. So how does CNN address this issue? And so we have two issues right here with scaling as well as translation. And so CNNs address both of these, I guess, in a really cool way that fully connected layers don't do. So first is sparse connectivity. And so our fully connected layers, basically each node in like layer 1 has taken input from every node in layer 0, right? So it's fully connected. As a result, I guess every node takes in the entire image of a sense as input, right? But with sparse connectivity, we're not doing that anymore, right? We're only focusing on like a set subset of an image, or input volume to be more precise, to, I guess, use for inputs. And so as a result, we can focus more on certain sections, I guess, in relation to their context, and thus we'll either I guess get rid of part of the problem of not scaling that well because of the fact that we can analyze bigger images without that risk. Next is parameter sharing. And so our second problem is that we're sensitive to translation. And a big reason to that is because we're weighing, in our old model, fully connected model, our end output is going to weigh each pixel by a certain weight and get that certain output. But if each pixel is weighed by a certain amount, then moving, I guess, like a thing in a picture is going to make it no longer classified the same. And so the way we fix that is called parameter sharing. And so the way we do that in CNN is that we're going to use the same weight matrix or filter in our convolutional layer to basically, we're going to use it for multiple sections of our image. And so you can think of it basically as sharing weights among different parts of our image. And so as a result, if we have the same weights being used in some sense for multiple parts of our input volume, we're no longer sensitive to translation because we're using the same weights everywhere. All right, now it's slide 25 because I can't count. So yeah, I'll pass it on to Angeline here.
All right, perfect. So now that we've kind of gone over the general idea of like what a CNN is and why we use it and why it's so important, let's now take a deeper dive into the more specific components of what exactly makes up a convolutional neural network. So once again, here's the architecture. And as you may notice, it actually looks quite similar to, a classic vanilla neural network because we have our input layer, our fully connected layers, and then our like softmax layer. But if you guys notice, we also do have a couple little extra layers that essentially allow the computer to be able to like see these images and gather data and make connections. So at least for this section, we're going to mainly be focusing on the first initial step. So how exactly do we get from the input to the convolutional layer? And so it will be like the first step. Okay, so before we are able to answer that question, we kind of have to understand how exactly does a computer approach an image? And to see that, we actually have this pretty cool demo that some really cool AI officers and I think TeachLA officers put together that could help us. So yeah, okay. I think we click next, yeah. All right, so let's just pretend that we're essentially the computer and we're presented with an input image, which is this section. And then so Nikhil, if you're able to just like hover your mouse like over it real quick. Right, just the first layer. So as you can see, we're slowly uncovering bit by bit small sections of this image. And kind of based on what you guys see so far, could you kind of tell us what do you think this image is? Like it could just be like, oh, is it a plant? Is it an animal, like a boat or something? Yeah, okay, cool. Yeah, so you guys are kind of picking up on like the little details that you're seeing just from this very specific image. And then so let's go into like the next layer and see if there's like anything else that we can kind of pick up on. Yeah, exactly. So now you guys are kind of seeing like smaller clues and hints, like Jeffrey said that there might be some ears. And so I guess like we probably just need to do like one more layer. Yeah, exactly. So essentially, this is kind of how the computer reads an image. So unlike us humans, where we kind of like take the image in full, the computer actually goes like section by section, and it will kind of like parse through like what it sees between the pixels, and then it creates these relationships, and then it processes these like patterns that it sees, and then it's able to kind of like spit out like an output. So if we go to the next slide, essentially the little like magnifying glass that we had, we call it a local receptive field. And essentially what a local receptive field is that it just kind of sections off a very small piece of the overall input layer. So all of the input neurons, you guys can think of just like the entire input image. And then the neurons would be like the individual pixels. And then, so if we go to the next slide, and so this essentially is just what a convolutional layer is. So as you can see that in this image, the first neuron in the first hidden layer is going to be responsible for just those first, that little box of neurons that you see over there, which is our local receptive field. And so all of the data that the computer is able to kind of like pick out and generate from that layer or that little section is going to go into that neuron. And so in order to kind of like get the overall picture, the computer can't just look at that tiny, 5x5 section. It actually has to go through the entire input layer. And to do that, the computer is going to shift the little local receptive field, or what we call a filter, over by one. And it's going to take that next section of like 25 neurons, and it's going to put all of the data that it filtered out into the second neuron. And so essentially what it does is that it's just going to go through every single like neuron across and down and put all of the data into the first hidden layer. And so that essentially is what a filter is. All right, yeah. And so just, I guess, like a more formalized definition, a filter is just a volume of weights that moves across an input volume and performs element-wise multiplication at every place it stops. We'll get more in depth into like the element-wise multiplication, but just the big idea of what that picture or diagram was just supposed to tell you guys is just how a computer is able to kind of read and process an image. And so the way that a filter moves is with a stride. And so a stride essentially just tells the filter how many pixels it should move over for every single neuron. So if we have a stride of 1, that means for every neuron, we'll move over 1 pixel. If we have a stride of 2, then instead of just 1 pixel, we'll move over 2 pixels. All right, so that's essentially kind of like what the big idea of a filter is. Okay. All right, so now that we kind of know like what a filter does and how it moves, let's kind of take a deeper look on how exactly does a filter kind of like gather the data. So as you can see in this filter diagram, we have a filter that is 3x3, and it's moving along the image. And so if you guys notice the little red numbers in the filter, right? So those are going to be our weights. And so the weights are essentially going to go onto every single part of the image. And it's just going to kind of apply that weight to that neuron. And then we're going to take all of those weights that we get from that one 3x3. So we'll have like 9 weights in total. We'll add a bias to it, and then that will be going into the neuron that we want it to go into. And then so essentially what this kind of shows is how filters really help with the issue of translation, because as Nikhil said earlier, as you can notice that the weights don't really change whenever we move the filter around. And so the reason why this is significant is because let's say that this filter is responsible for looking for maybe like the ear of a cat. So if the cat's ear is at the very top left corner, or if it's at the very like bottom right corner, because the weights are the same, no matter where the ear is, we're eventually going to find it. Because having the same weights, no matter where you go along the image, means that eventually it's going to light up at some point based on like the multiplication that we do, which is really big, because translation is something that we try to not be like super sensitive to. Okay. All right. And then so just to make sure that you guys are kind of following along, could you tell us what the stride of this filter is, and I guess like the size of the filter? Yeah, perfect. You guys seem to be getting it. Yeah, so this filter has a stride of 1, because if you notice, it moves over once each time per neuron. And then the size would be 3 by 3 because it is 3 neurons wide. And yeah, you guys pretty much got it. All right, perfect. And so if you guys noticed in the diagram that we showed originally, the convolutional layer looked like it had some depth to it. However, whenever we pass a filter over an image, the feature map that we produce is 2D. So how exactly do we go from a 2D feature map to a 3D convolutional layer? Well, essentially, the diagram that we were showing you guys earlier was just one filter. And so when we're actually passing an image through a convolutional layer, we're not just applying one filter, we actually apply multiple filters to the image at the same time. And so what this does is that it would produce multiple feature maps. So one filter produces one feature map. So that means if we have 2 filters, then we'll get 2 feature maps, and then so on and so forth. So essentially what this diagram shows is that like, we have 3 filters, and then we have 3 feature maps. And then to get that 3D output, we essentially just stack all of the feature maps together, and now we have a depth of 3. Yeah, and so this is just kind of like a summary of everything. Essentially, a filter is a 3D volume 2. So we were working kind of with a monochrome image, so that had a depth of 1. However, if we have a colored image, that's going to have a depth of 3, right, in the input layer, because you have the red, the blue, and the green. And because the input layer has a depth of 3, that means our filter will also need to have a depth of 3 too. And so that's essentially what it kind of means when it says that a filter is also a 3D volume. So just remember that the filter's depth has to match the depth of the input volume. But the final feature map is going to be a 2D volume just by itself. And then essentially, yeah, so that's basically what like the third bullet point is saying on how the depth of the filter has to match the depth of the input layer. All right, perfect. So just a quick discussion, just to make sure that we're all on track. What sort of task is a convolutional neural network best suited for? Yeah, perfect. Yeah, Margaret and Jeffrey, you guys hit it spot on. Yeah, essentially convolutional neural networks are mainly used for like image recognition and like image classification. All right. So for the second question, consider a color image. What would the dimensions of the input model be? Yeah, perfect. Exactly. Because a colored image, because it does have the red, the blue, and the green, we need, I guess, like a layer for each one of those. So naturally, it would have a depth of 3. So you guys got it. Perfect. And then I guess so the third question is, what is a filter? Yeah, this one's a little bit more complicated, I would say. Yeah, perfect. You guys got it spot on. Yeah, so it's essentially just a local receptive field that kind of takes the image, the input image in sections, and it's able to like extract like very specific features and kind of like make kind of like identify patterns between pixels. Yeah, okay. So Terry asked if CNNs can support like more dimensions than just 3. So yeah, technically you can have like as many like dimensions as like you need, but I think usually they kind of typically the input dimensions would have like a depth of 3 if it's like just like a normal like colored image. Okay, and then I guess for our final question, what exactly is a stride? Yeah, perfect. You guys got it. Good job. All right, so now we're going to just kind of talk about feature maps, just like a little review. So essentially, a feature map is the product of everything that the filter scans. And the most important thing to kind of remember is that every filter will produce one feature map, and that one feature map is going to be a 2D output. So even though the input layer might have like a depth of 3, if you apply like one filter on it, the feature map that is produced just by applying the filter is going to be 2D rather than having like multiple like dimensions. And the only way that we're able to kind of get the depth that we need for like a convolutional layer is when we apply multiple filters on top of the input layer and then stack them on top of each other to get that 3D output that we need. Yeah, essentially. Yeah, so this is pretty much what like a convolutional layer is. So a convolutional layer just consists of multiple filters that we kind of go over the initial input layer with, and that itself will produce an output volume. And so each filter is responsible for just kind of looking for a very specific feature. And these features are usually very like low level kind of patterns. Sometimes they're so like low level that like us humans aren't even able to pick up on. Yeah, and then so essentially, there's no kind of like set amount of like filters that you can use. So this is like something that you can kind of decide for yourself based on the model that you're creating. Yeah, and then so this is kind of just like a nice visualization on how filters kind of work. So if you kind of see this mouse, right? And then so let's say that this filter, as you can see, the filter is going to be the table that's on the right. That's like the pixel representation of a filter. And so as you can see, the filter has weights applied to it where you have like the 30s. And if you kind of notice the way that it's structured, it's kind of looking for a very specific feature, which kind of like resembles like a curve. So this kind of tells you that this specific filter is just looking for the curve of the mouse. And then so if you go to the left table, this is a pixel representation of like the receptive field. So let's say that the filter has just been moving across the image and it has finally come to this section that you see on the left. So when the filter is applied onto that section, it's going to do element-wise multiplication on every single one of the boxes. And if you notice at the bottom, after it's kind of like done with the whole like element-wise multiplication, it gets all added together and then we get a very large number. And so what this number kind of essentially tells the model is that, hey, there actually might be something here, or like there might be this very specific feature here. And so this is kind of the way that the model is able to kind of gather up clues when looking through the image to make its final decision on what it thinks this image is. Perfect. Okay. And then so just kind of like big picture things on like why filters are important. I guess one of like the big things is that filters allow the computer to kind of figure out the relationship between pixels in a very efficient way, which is needed for images. And then filters look for features. And then, yeah, and since the filters all have the same weight applied to them, it means that this model, CNNs, are very unsensitive. They're not sensitive to translation, which is something that is very important. Yeah, and essentially when it comes to like filters, strides, and padding, which is something we'll talk about like right after this, these are known as hyperparameters. So the computer doesn't decide this stuff for you. You actually have to kind of figure it out yourself. And yeah, so essentially when you're like training the model, these are things that you can kind of play with to figure out which one gives you the best output. All right, perfect. And then I'll pass it on to Preetham.
All right, so volume is essentially a stack of features. Okay, so all right, so that's true. And we'll go to zero padding. Sorry for the voice. Okay, so zero padding is basically really good. So when you have like a smaller image to scale it up, so instead of using scaling to make the image bigger, you could use zero padding to preserve your patterns in the image so you don't run the risk of losing it. And it can also help to speed your computation while passing images in your convolutional neural network. So other advantages of zero padding include that we may want to output volume to have particular spatial arrangement. So like I said, maybe we want a larger output volume, but we have a small image. So that's one way zero padding can help. And so what exactly is zero padding? So we've talked about all the advantages first. So let's actually get down to what it actually is. So we add zeros around the edges of the input volume. So it's like a pad that kind of like preserves the original image without like modifying it too much, so we don't run the risk of maybe like destroying any patterns that the computer wants to learn. Maybe like, for example, we had the koala image. Maybe that's a small image, but when we scaled it up to a much larger size, we had maybe one of the features getting lengthened out or losing clarity. And that could be a huge risk. And the optimal way to figure out the volume size would be the floor of W minus F plus 2P over S and then plus 1. So what are these exactly? So W would be the input volume size, the volume as we discussed, a stack of feature maps, and the size of that. F would be the filter size, so n by n, the n in the filter, and p would be the 0 padding size that you want, and s would be the stride size, the one in our like 3x3 moving image, or whatever you want the stride to be. Yep. So, all right. So this would be a visualization of a multi-filter. So you could see that there's like many filters moving in these images. So we have like in the 0 padding image, we have the square moving from left to right, and as well as the output volume having the squares moving from left to right as well. So that could be like the multi-filter for a padded image, and using multiple filters to do this. All right, so this would be the first layer for the data set given the ImageNet neural network that is very famous for its research. So, and we've just talked about 0 padding and multi-filters and how that could help for feature detection and image processing. So do you guys have any questions on what we've covered so far?
How do you know what the edges of an input volume are?
But could you like speak a little louder?
Sorry. So you know how in zero padding, you were talking about how we have to add zeros around edges of
Yeah.
input volume.
Mhm.
What are these edges, and like how do you find them?
Okay, so let's say we want our like output volume to be bigger than our image size. So let's say we had a 3x3 image or something, like sorry, it wouldn't be 3x3, but it would be some number of pixels by some number of pixels, but we wanted something that would be larger. So we want that amount of pixels, like the larger amount, without actually like damaging any like features that were in our original image. And that's kind of how we like figure out our edges and scale to a larger image, if that kind of makes sense. So in this picture right here, you could see like the zeros are on the edges, and like our original edges would be like the 0, 0, 1, 0, 2, and down to the sides and the bottom. Does that kind of make sense? Or
I don't know, because like the output volume looks pretty
Mhm.
small to me.
Oh, okay. Oh, yeah. Sorry, I didn't mean the output volume, but like we want our images to be the same scale is what I meant. Like we want it to be a certain image size. That's what I meant. Sorry, not the output volume. If that
But
was your question, was that it? Or
I
I
don't
was
know what I asked, so
using
it's
the
fine.
wrong word. So sorry about that. All right, I guess we can move on. All right, so let's go to our other layers. So we talked about our general layer patterns or the architecture. So we had our convolutional layer, so convolution layer. So that would be the layer that handles all the like convolutions to the data, and maybe like the translation or adaptations to other like other things that happen, like maybe rotation or like I don't know, any like translation in general. And we talked about, we're going to talk about Rayleigh. So what Rayleigh does is it speeds up the computation, and it also does other things like um, fix the vanishing gradient problem and all that. So we'll move on to that. So what exactly is Rayleigh? So Rayleigh is a nonlinear layer, and we're gonna speak about what it is and what what about its shape is really important to what we're going to talk about. So we apply Rayleigh to the output of our convolutional layers. So we want to ask ourselves why we use Rayleigh. So why we would use Rayleigh is because it has a small range for our sigmoid, and it actually leads to a vanishing gradient. So our sigmoid at first has a small range, and this leads to a vanishing gradient, which is a problem. So we would want Rayleigh to fix it, because Rayleigh gradient values are larger in general, and it can also kill neurons, which can add to this vanishing gradient problem. So that's one way that Rayleigh can help. And not mentioned here, but I guess you could find this online or like with your own research, but Rayleigh also speeds up computation, which would take more time in a general convolutional neural network without it, as well as fixing the vanishing gradient problem. We again have this overview of our general layers in our convolutional neural network. So I know like maybe this image is like getting repeated a lot. So why we're showing this is, as we're going over each layer, we want to show a high level overview of how things relate to one another as we learn each layer. So the next one would be our max pooling layer, and or max pool layer as it's called. So what it does. So what are our like goals for having a pooling layer? So we want to reduce the spatial size of features. So we want to reduce this so that it doesn't harm our computation, and it like lowers the computing intensive power that we need. And we also want to control overfitting that maybe the fully connected layers or the other layers gave rise to, as well as reducing the amount of parameters that we have. Okay, so max pooling. So what does this actually do like on a high level? So we take the maximum value from each section of this. So let's say we have 6, 8. So we take the maximum from each part. So each part of this 2 by 2. So we have 6 from 1, 1, 5, 6. We have 8 from 2, 4, 7, 8, and 3 from this section. And from the blue section, we would have 4. So in this case, the filter size would be 2. So as we move along this, we would have a filter size of 2, and our stride would be 2. So let's say we started from our left side along, right on the border of the x-axis. So we'd have 1, 1, 5, 6 be our first filter part, and then we would move over by 2. So we would get to the 2, 7, and so on and so forth. And what we're doing here is we're downsampling by 75%. So what that exactly means is we're reducing each of these dimensions, the 224, that's actually by half, but yeah, so we would downsample by 75% as well. All right. So another way of doing this is average pooling. So we talked about max pooling before, but we could also do average pooling. So from each filter part here, so we would do 0, 0, 2, 2, and we would take the average of this. So same thing here. So we would move by 2 for each stride. So we would start at 0, 0, 2, 2 on the orange, and we would go to the gray, the yellow, then the green. So let's just kind of walk through this. So we'd have 0, 0, 2, 2, that average out to 1, because 0 plus 2 plus 2 over 4 would be 1. Similarly for this, it would be 5. For this, it would be 6 and 2 and so on. So that's average pooling. And like it says, average for each of the F by F sections, or the 2 by 2 sections here. Okay, so we have some certain common practices. So we could use any parameter like Angeline said. So that would be your hyperparameters. But in our examples, we chose F equals 2 and S equals 2. Filter size would be the N by N or the 2 by 2. And our S stride would be how much we move over. So if we use f equals 3 in the images or the examples we went over, we would have one column overlapping. So that's called overlapping pooling. That's how it gets its name. And how about pooling? So why we want to like avoid pooling in this layer? Sorry, padding in the pooling layer. It's because so it's kind of uncommon to do this in general, and it could harm our averages. So let's say we decided to use our average pooling layer, like average pooling. And if we use padding in that, it would harm our like average. So if we include zeros in our average, it would bring your average down and could harm a feature or harm our predictions. So another thing to consider is that the max pooling generally performs best in practice. It could be because the average could go down based on the other numbers in our examples. So referring back to the examples again, but that's one of the reasons that the max pooling generally performs better. And it makes the program more decisive. So it doesn't take into consideration lower clarity pixels and stuff like that. So let's look at an example with max pooling and after average pooling. So we want to consider both the advantages and disadvantages of both types of pooling. So let's say we have an input feature map of a, I don't know, like a line running through, a black line running through a white box. So after max pooling, we would just have a white image, because if we just run through this example here, so 0, 255, 255, and 0, we would not get a black line. We would just end up with white. And that could be one of the drawbacks of max pooling. But with average pooling, we have a gray image. So it takes the averages and it would produce a better recreation of this image. But so this is when we have white as our background. But when we use black as our background, we would end up getting a better image for max pooling, and besides when compared to average pooling. So that would be our image. So both of them have drawbacks. One's not completely perfect, but we would generally use max pooling in general because we would have darker backgrounds. So yeah. All right. So let's run through some questions and kind of test our understanding as we go through. So what is the purpose of a pooling layer? So you could type this in the chat or aloud, whatever works for you. But what is the purpose of a pooling layer would be our first question. And why might it be okay that we lose information during pooling? So for number 2, we could like weigh the advantages and disadvantages of average pooling and max pooling. So someone in the chat said save computation time. So that could be one of our advantages. So anyone else? Okay, so yeah, Jeffrey also said overfitting is a thing too. So that's another thing to consider. Yep. Anyone else besides Jeffrey want to say anything? Okay, so someone said, what is overfitting? So maybe let's take the example of the cat. So in general, so overfitting could be that the cat on the left in our examples was predicted correctly because we gave examples of the same cat or the same image, but let's say we shifted the cat over to the left. So our machine, like our algorithms, our learning not being able to detect the cat shifted to the left would be an example of overfitting. So this is in context to images, but overfitting in general is basically like catering like our learning so deeply into our training data that we don't like generalize enough to predict our either test data or real life data well enough. So I guess that should answer what overfitting is. All right, so I think people answered both questions, but if there's anyone else, they could answer because we only had like one answer to the question. All right, so I guess Jeffrey did a good job on doing things. So if you want to have more information to these, to either pooling or downsampling, or maybe even learning about stride, there are links on the bottom of these slides, of this slide. So you could check those out. All right. So again, we have our general architecture to kind of sum up what we said about each of our layers in general to the whole neural network. So we have our fully connected layers and our softmax. So I don't know if we remember our softmax from the beginning of our lecture series. So softmax kind of generalizes to many outputs rather than just two. So that's just kind of review. So making predictions. So we need some way to take these 3D tensors and kind of go to one vector that, so for example, let's say that this would be, so like Nikhil said that we would also cover softmax in detail next week, so that's good too. So let's say the right would be our feature, not a feature vector, but our output vector. So maybe the probabilities of each class in the classification resulting could be an example of what the softmax does. So just jumping back to this, for vanilla neural networks, softmax was also used. So it's kind of like this. So we input a vector and we want each element to correspond to a class. So in this example, let's say maybe the right-hand side would be the probabilities of which classes each or that image corresponds to. So maybe like 0.46 would be more more for the first class than the second or the third class. So that could be one example. Yeah, so outputs vector probabilities for each class. And convolutional layers, like we said, don't output vectors, so they output something 3D or tensors, and we want to convert that output into a vector. Yep. And let's jump into our fully connected layer. So fully connected layers have, so basically it's kind of our vanilla neural network kind of layers that have connections from one neuron to every other neuron. So they're fully connected, just like the name. And they forward propagate the flattened output. And they do this through the FC layers or the fully connected layers, just like we had in our vanilla neural network. So just kind of like a review, but a CNN is also a neural network and it does share something with other neural networks as well. Yep. All right, so yeah, so I did miss an important part about fully connected layers. So it does unroll the output and make it better for our output in the future. So our last part would be our softmax function, and we'll go into that probably deeper next week, but what it does is it basically makes it so that the CNN can output our predictions, and we can choose maybe like boat, which has 0.94 in the examples, if you can see that, in comparison to the dog, cat, or the bird. So, all right, so we talked about MNIST. So what is MNIST? MNIST is a large database of handwritten digits, and it's one of the more famous problems that CNNs first solved. And researchers have been able to accomplish recognizing these handwritten digits with error rates as low as 0.23% with convolutional neural networks. So what does this mean for CNNs in general? So CNNs have progressed, and if researchers have been able to do this, it kind of justifies the point of having CNNs do image identification, and not only image identification, but other tasks as well, but image identification in significance, and more importantly, that task for other applications as well. So what is Alexnet? So we've just talked about convolutional neural networks in general, but there are other convolutional neural networks that people have built upon the general foundation to make them better. So we have a convolutional neural network designed by Alex Krzyzewski. I don't know if I said that name right, but in his research paper titled ImageNet Classification with Deep Convolutional Neural Networks, it was very influential, and it pioneered the use of CNNs, and it was also used to win the 2012 ImageNet Large Scale Visual Recognition Challenge. So it's not only Alexnet, but there are other convolutional neural networks that have built on CNNs, or this one in particular pioneered the use of CNNs, but people have been building upon them. So you can probably find that online too with other research papers as well. So let's talk about how Alexnet was built, like what layers it had, what was the structure of the network in general. So we had Alexnet had 5 convolutional layers and 3 fully connected layers. So what we talked about today, and we had Rayleigh is applied after each convolutional or fully connected layer. So to minimize our vanishing gradient problem and to speed up computation. And we have dropout being applied before each of the first 2 fully connected layers. So, and we have max pooling. So what we talked about towards the end of our lecture series. And so this is kind of general discussion about the whole lecture in general, or whole workshop in general. So why are filters used for CNNs? What is the intuition between zero padding, and why we use Rayleigh? Why does the max pooling generally perform better than average pooling in practice? So all these are questions that are open for discussion, and you can just go ahead and answer in slides and answer with your voice too. Both work. All right, so if no one actually wants to answer, we can just go over these.
I'm typing.
What? Sorry.
I'm typing.
Oh.
Or
sorry.
do you want me to just say it out loud?
Either way works. Yeah, go ahead.
I think the first one is to create feature maps.
Okay. All right. Yeah. So it could also reduce the number of weights that we got to account for and better detect relationships between nearby pixels. So in addition to what you said, scanning for features and building feature maps. So do you want to answer other ones or? But your answer was valid too, so.
What do you want me to ask the rest of the questions too?
It's up to you.
I could. The second one I'm not too sure because I don't fully get it, but I think it's so you can control your, like, given your input layer, like you can control the size of your output better.
Okay, yeah. So yep. So we wanted our outputs from a particular layer to exhibit some dimensionality. So we want some dimension from one layer to the next. So that could be valid. So yep. Anyone else want to answer this question or the other ones? We'll go through each question one by one though. So is everyone good on why we use zero padding and why we want a certain dimension from one layer to the next and why we add zeros around edges of our input volume? All right, I'll just take it as a yes to go on to number 3. So why Rayleigh? So what's the use of Rayleigh in our CNN in general? Okay, so Terry put in the chat that Rayleigh has a larger gradient than sigmoid, so we avoid vanishing gradients. So that is a great answer, and that is one of the reasons why we use Rayleigh. Yeah, just adding to that, that's most of it. But just adding to why Rayleigh, it also speeds up our computation time in our CNNs as well. That's just an added benefit, but what Terry said would be one of the major reasons. And number 4. So why does max pooling generally perform better than average pooling in practice? So, all right. So Margaret said that max pooling is more decisive. Does anyone have other reasons why? Or? All right, so Jeffrey said that average pooling is affected by unrelated surrounding pixels. So that's also true. So average pooling doesn't efficiently preserve needed features in computer vision. So that's another reason why. And it also relates to that max pooling is more decisive. All right. So do you guys have any questions in general? Or?
I mean, I had a lot of questions, but we can wait until after.
Oh, okay, sure, yeah. All right. Then, well, thank you all for coming today. So we have our anonymous feedback form and we would like you to fill it out. And if you haven't already checked out our Facebook group, so you could also check that out. And in addition to all this, we do have one thing in addition to all this. That would be our Conda environment setup. So we would like you to read through and complete the steps on this document. So what this is for our workshops in the future where we're going to be doing a more hands-on computer vision example project and our guided project at the end of our workshop. So we're still on our third workshop, but we would like this to be done by the sixth workshop. And if you have any like questions or comments about this in general, you could ask us on the Discord or during one of our workshops, assuming after this one, if you haven't done this already. Yep. And there are other resources that you can check out. Yeah, so you could check out any of these great resources to kind of complement our workshop. So we kind of covered the foundations of CNNs, but there are more to CNNs in general, and it has been an expanding field. So any of these resources can kind of get you up to level or educate you deeper on the subject. Yep. And in general, thank you for attending our third workshop, and we do look forward to seeing you in later workshops.